Okay, so we finished talking about the single delay feedback filters. And we saw by making a simple change, instead of having xn plus some lag of x, if we do a lag of y, the output, and we feed that output at a previous time back into the output at a later time, then we can get some very interesting effects, and certain frequencies actually blow up if we have this alpha greater than or equal to 1. And I showed that you could understand that mathematically by looking at the z transform and looking at the locations of these poles, or z's that you can feed into this that make the denominator of this go to 0. One more quick thing I wanted to mention about this is if you take this and rearrange it and use some of the tricks that we've seen before, you can actually separate out the phase portion of this and the magnitude portion, and you see this expression showing up in the denominator. And this explains why. So if w tau is equal to 2 pi times k, then this sign in the denominator is going to be 0. That's why the thing blows up. And so when I had this example of, it's worth actually plotting this for example, we'll say t is equal to 10. Let me look at all the possible radian frequencies from 0 to pi. And in fact, let me convert that to units of cycles per sample rather than radians per sample. So I'll say, here, let me divide this by 2 pi. So if I plot f versus 1 over 2 sine omega times tau over, or t over 2. Oops, I had to change this to space 1,000 frequencies, and I don't want to go all the way up to pi because that's for sure going to be a divide by 0 here. So anyway, when I look at this and I look at the magnitude, the absolute value of this, I see this pattern here. And what I'm seeing is these are really points of infinity. It goes to infinity when I go through 0.1 cycles per sample, which makes perfect sense because that's the frequency associated to a period of 10 samples. And I also get the same thing happening at all the harmonics. If I were to change this to, let's say, 5, then I would see one of these peaks every 0.2 cycles per sample. If I changed it to 20, I would see one every 0.05. So I just want to point out that actually makes sense. This is where it goes to infinity, and we see that. It's like taking the unit circle that I was showing before. Where'd it go? It's like taking the unit circle that I was showing before where I was in the z-plane, and unwrapping that circle, the upper semicircle. It's like plotting that down here. Okay, so now that we've done that, I want to generalize beyond a single feedback term. And I want to write a general form of a difference equation here. So what I'm going to say is the following. I'm going to say A0 times yn equals, I'll say here b0 times xn plus b1 times xn minus 1 plus b2 times xn minus 2, da da da. We can have as many of these terms as we want. These are called the feed forward terms. This is what we were used to. We can represent this as just an ordinary finite impulse response. But then we also have the feedback terms. And actually, I'm going to put the feedback terms, I'm going to subtract them for reasons that will become clear in a moment. But I'm going to say here, okay, this is going to be minus a1 times y n minus 1 plus a2 times y n minus 2 plus a3 y n minus 3, so on and so forth. Okay, so this is the general form of a difference equation. Now, what I can do is, if I move these coefficients over to this side of the equation, I can rewrite this as a0 yn plus a1 yn minus 1 plus all that equals bn. Okay, so I just added this to both sides. Okay, so what I really want to do here is solve for y of n, and I can do this by taking the z transform of both sides. And what we know is every time we have a lag, that's just like multiplying by e to the negative j omega, or z to the negative 1, if you're looking at the general z transform. So yeah, actually let me write it in a general way first. So I'll say, okay, let's make this So that would be a0 yn plus a1 yn times z to the negative 1, right? Plus a2 yn times z to the negative 2, so on and so forth, equals b0 xn plus b1 xn times e to the, or z to the negative 1 plus b2 z, xn z to the negative 2. Right, so this is how the z transform would go. Every time we see a lag, we multiply by another factor of z to the negative 1. That's just a nice thing we get with these complex numbers here. And so now what I can do is factor y out on the left side of this equation and factor x out on the right side of the equation. So what we'll get here is, okay, this is going to be yn times a0 plus a1 z to the negative 1 plus a2 z to the negative 2, so on and so forth, is equal to xn times b0 plus b1 z to the negative 1 plus b2 z to the negative 2, so on and so forth. And now we have a clear path for solving for yn in terms of xn. So we're going to make what we call the transfer function, which tells us, okay, when I give you an input phasor xn, what do I expect from the output phasor yn? And so in general, this is going to be a fraction where I put this, the feed forward or the convolutional terms in the numerator, and then the feedback terms are in the denominator. So here's what it looks like. And this is the general form of the z transform. Okay, so just as a sanity check, let's look at the example that we had before. And if I put it into this form, what I realize is, okay, it's actually supposed to be minus all the y terms. So I'll do minus, this is a little bit weird, but minus negative alpha. That's the same thing as plus alpha. And then what I can do is take this equation and say, okay, I have, so a of 0 in front of yn here, that's just 1. So, and then I've got b of 0 is 1 and no other b's. So what I end up with here is the transfer function, which is, okay, so b of 0 is 1, none of the other b's or anything. A of 0 is 1, as I said. And then we have the only term here that's non-zero is a of t. So a of t here is negative alpha. So I'll just say 1 minus alpha times z to the negative t. Okay. So if I look at that, does that match up with what I had before? 1 over 1 minus, and it sure does. Okay. All right, but we can do this on a fancy example. So let's take this example here. I've actually got 3 feedback terms. And if I go up and I fill in the transfer function according to my derivation, so if I do the z transform, my numerator is the same as before because I just have one term xn there. But the denominator here is going to be, okay, so a0 is 1, right? So coefficient in front of yn. Then I've got a negative 1 with a lag of 2, so that would be minus z to the negative 2. I've got a negative 1 with a lag of 3, so that would be minus z to the negative 3. And then I've got a positive 1 with a lag of 5, so that would be plus z to the negative 5. And if I look at this, I see this is a polynomial equation in z to the negative 1. And in fact, I set this up on purpose so that I could factor it. And I can factor this into the quantity 1 minus z to the negative 2 times the quantity 1 minus z to the negative 3. And you'll notice I get this polynomial. But here it's easier to see what the poles are. Okay, so let's try to look at this numerically. I'm going to take the one lag filter code that I had before and generalize it. I'll call it a valve filter. And I'm going to follow conventions that scipy signal uses. I'm going to pass along the array of b's, the array of a's, and then the signal x that I want to filter. And so let me just say, keep it simple, I'll just make y the same length as x for now. And okay, let me get this equation here so I have the general form that I need. So I'm trying to create a yn here. And so if I'm just evaluating this in the time domain, what I need to do is first loop through feed forward, or just ordinary convolutional lag terms in x. So I'll say here if, or I'll say for I in range len of b. So let me go through all the feed forward terms. And here I'll say if I is less than n, or less than or equal to n, then yi plus equals bi times xi. Okay, so if I can go that far in the past, then grab the x in the past and multiply it by b of I. Okay, next thing I need to do is loop through the feed back terms. So these are lags of x, or sorry, lags of y. So now I'll say, okay, for I in range, I'm going to say, let me say 1 length of a. I'm going to deal with a of 0 separately. But I'll go from 1 to length of a. And similar kind of thing, I'll say if I is less than or equal to n, and I can go ahead and accumulate the previous y. So here I'll say this should now be a I times y of n minus I. Oh, I had a little mistake up here. I meant to say here, this is n minus I, right? Okay, good. So x of n minus I looks right. So we get x of n, x of n minus 1, x of n minus 2. And down here we get y of n minus 1, y of n minus 2. And then the last thing we have to do, because we have this a of 0 hanging off in the front here, we have to divide the whole thing at the end of this. I'm going to have to say that y of n is divided by a of 0. So I better make sure that a of 0, it doesn't really make sense if, I'll just make sure that a of 0 is not equal to 0. Okay. All right, so that's the equation to evaluate this. Let me just quickly check this on the example here. So I'm going to put in here, so my a for this example would be 1, and then a bunch of zeros, and then negative alpha. Okay, so I'm going to say a here is equal to np dot zeros. Let's say t is equal to 10. T plus 1, a0 equals 1, and then a t is equal to negative alpha. Okay, so we're going to do that. And then my b is really simple. It's just 1. Okay. So if I, and let's say x, so the x's that blew this up before, that was these ones, so let me just copy this. And I'm just going to make sure that it looks the same. So this is the first example here. So we got that, and so let me go ahead and send that through. Say y is equal to eval filter bax. Hopefully this worked. Okay. Now I plot this. Something is a little bit off here. Let me just double check my code here for a second. Okay, I actually made 2 little mistakes here. One is this should be a y of n. Okay, I'm trying to accumulate this at time n. And the other thing is, if I'm really following this equation down to the letter, this needs to be a negative sign. And that's just because I was being really careful because I wanted the expression of the z transform to end up so that I could put all the a's in just as they were in the denominator and all the b's in just as they were in the numerator. And this is the convention that's followed by everybody else. So if I update this, then I get this. Okay, and this is starting to look a lot more like what we had before. If I make alpha equal to 1, then I get this thing that blows up. Okay, that's great. What about the transfer function? So now I'm going to say, okay, let's get the transfer function. So that's just the quotient of the z transform of the feed forward terms over the z transform of the feedback terms. Or in other words, it's exactly the complex number that you would get that affects x, depending on whatever x is. So that's this here. Let me bring this down. And okay, so what I want to do is I want to, so I'm going to pass in a particular z here. So I'll pass in my b, my a, and some z. And let me add up all of the terms in the numerator. So I'll say, okay, my result is equal to, starts with 0 plus 0i. I'll say for I in range length of b, I'll say regret plus equals b of I times z raised to the negative I. And actually, let me just say that that'll be the numerator. And then I'll make the denominator in much the same way, except I'll be using the a terms here. So this will be the denominator plus equals, so I'll go through the a's, and I'll say this is a of I times z negative I. And then finally, I'm just going to return the numerator over the denominator. Okay, now if I do that thing where I evaluate this transfer function on the upper semicircle, so from 0 to pi, then I can look at what the response is for all the possible frequencies I could have. And so let me actually, I'll plot this in units of samples per cycle once again. Or, sorry, cycles per sample. And so once again, I see this nice plot. So that's all matching up with what I had before. Yeah, if I change this back to 10, we should see these plots look nearly identical. You know, these are points of infinity, so it just depends on exactly where I evaluate that. But yeah, once again, I see them peaking at the right spot. And this matches up well with what I was looking at before when I plotted the magnitude Z transform in the complex plane, and I could see where those poles were on the upper semicircle there. Okay. Now let me do a similar thing where I plot the magnitudes of the Z transform for this other example I made here, where I had these 3 lags. And I saw that the Z transform looked like this, and I was able to factorize it like this. If I plot the magnitude of the Z transform for that one, I get a picture like this. And it looks like there's 4 poles, although you have to be a little bit careful. So if I look back at this equation, and I look at each of these terms that I factorized into, I can actually see there are 2 roots of this first term here. So 0 and pi will make this first term 0. And there's actually 3 roots of this one, 0, 2 pi over 3, and 4 pi over 3. And so what we see is in total this has 5 roots. And that's no coincidence. This is a consequence of the fundamental theorem of algebra, which says this is a degree 5 polynomial, so it's going to have 5 roots in the complex plane. Some of those roots may be repeated. In this case, the root of 1 shows up twice. It shows up here and it shows up here. And that's why when I look at this, it looks like the pole at 1 is extra strong. I mean, they all go to infinity, but this one goes to infinity a little bit faster. So I have that repeated root here. Then I have the root of pi. And then I have the root 2 pi over 3, 4 pi over 3. And so this is really nice. And what we can say is this is just a fact of algebra, that there are going to be as many roots or as many poles here. So as many roots in the denominator, as many poles, as the maximum lag in our filter. So here the maximum lag is 5. And again, that matches up with even that single lag example I was looking at. When I had 10 lags in this example, I could see 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 poles. All right, so it's very cool. So the degree of the polynomial, or otherwise seen as the maximum lag, tells me exactly how many poles I'm going to have. We just have to be a little bit careful because some of them can be repeated. Oh, and I'd be remiss if I didn't mention an extremely important method that's part of the scipy signal class. And that is a method that automatically numerically computes the poles and also the zeros. Okay, so the poles are the roots of the polynomial in the denominator of this rational function for the transfer function here. The zeros are the roots of the polynomial in the numerator. So the poles pull the magnitude towards infinity, like the 10 poles. The zeros pull the magnitude down towards 0. So that's also possible. And so there's a method that will automatically solve those polynomial equations in the numerator and the denominator. So I'll say zeros, poles equals signal dot tf transfer function to z zeros, poles, and k. This is called the gain, but I don't care about that right now. So let me pass on BA here. And let me write a little bit of code to plot. So I'll say for z in zeros. Let me plot little dots. So I'll say plt.scatter, mp.real z, mp.imag z. Let me make them orange. And let me also plot the poles. And I'll plot those as x's. So I'll do this. I'll say marker equals x. Let me make these nice and big, actually. And I'm going to say real component of this pole, imaginary component of the pole. Okay, let's have a look at those. And so, actually, I don't see any zeros in this one, which makes sense because this particular example, I just had a 1 in the numerator. There's no real zeros, or there's just no zeros of that. But then I can see the poles are in the locations that I predicted they would be. But this actually solves for them explicitly, so that can be useful. All right, now we just did a lot of math, okay? So we know exactly how to compute the zeros and the poles for general difference equations now. They can have feed-forward, these convolutional terms. They can also have feedback terms now. But why did I do all this? Well, the reason is because, as I promised, if I understand feedback filters, I could design and analyze more efficient low-pass, bandpass, and high-pass filters. And in fact, what I'll do here, I'm going to use I'll treat this as a black box, something called a Butterworth filter in scipy, to design feedback filter coefficients for low-pass, bandpass, and high-pass filters. And I'll treat it as a black box for now. I'm not going to explain how this works, but I'm just going to look at what it returns. Because really, you might say, it's the bread and butter of filter design. Oh no. Crickets? Nobody liked that joke? Okay. All right. So let's look at how this works here. So the first parameter is the order of the filter. What this is the degree of the highest term in the polynomial. So you would say, like, if n is 10, then it can have z to the negative 10th in the numerator or the denominator. This here, if it's a low pass or a high pass filter, specifies the cutoff frequency, and I have to be a little bit careful here. It says between 0 and 1, where 1 is the Nyquist frequency. So actually, it's defined as half cycles per sample instead of cycles per sample. So be a little bit careful about that. And then, yeah, I'll say to output in BA. That's what we've been doing. Okay, so let's go back and do this. I'll say maybe let's make the order 5 to start with. I'll make the cutoff frequency be 0.1. This is going to be in cycles per sample, so I know I'm going to have to change that when I pass along. And then I'll say, okay, BA is equal to signal.butter n, and then W times 2, because again, they use slightly different units from me. I'm going to make this a low pass. Let me just double check that I got that. Yep, low pass, and then I'll say output equals BA. Okay, so let me do that, and I will just copy and paste this code here and see what are the poles and the zeros of this filter. Okay, so here it is. And so what I see a very interesting pattern. Actually, what I end up here, I should have 6 zeros and 6 poles because it goes up to z to the negative 5th, so including z to the 0, that is 6 terms here. So just to check, I can show you the length of B is 6. Okay, length of A is also 6. So numerator has 6 terms, denominator has 6 terms. So here are the poles, or the zeros of the denominator. And what I see is they're all kind of clustered around the origin. So I start here, okay, this is like a low frequency. This is 0 hertz, or 0 cycles per sample, or 0 cycles per radian, really, since I'm on the circle here. So now I go up, higher frequency. So I'm close to all these poles at the beginning, and they're pulling me up. But then I get further away from the poles and closer to the zeros, and the zeros pull me down. So that sounds an awful lot like a low-pass filter. For the low frequencies, it pulls me up, and for the higher frequencies, it pulls me down. And so let me go ahead and see if that's true. Let me plot the transfer function here, and I'll make sure it's in units of cycles per sample. Next label, yeah, cycles per sample. And this looks pretty promising. So if I plot where I wanted the cutoff to be, it was supposed to be at omega. And if I look at that, there we go. Okay, so nice cutoff. And I only had to look 5 terms into the past, right? This is order 5. That's another way of saying it. So this is how many terms in the past I need to look. Now, let's do a similar thing for feed-forward filter. And this is, I mean, if you go back to the other video, you can see how we did this, this filter design. I used the discrete Fourier transform actually to design a convolutional filter, just a feed-forward filter, like these things. And so I'm not going to go through that again here, but I'm just going to copy and paste a little bit of code to do this because I want to compare the efficiency of these two. So let's say here, okay, so let's try to use one with only 5 samples and see how that does, right? Because that would be like, or I guess I'll say 6. So that will go 5 samples into the past. So going an equal amount of time in the past, let's see how we do with this filter. Actually, by the way, I should really plot this in decibels here. I should really be plotting rather than plotting the absolute value of the transfer function directly, I should actually be plotting like the log of it, roughly, or maybe the log 10 of it. Or maybe I should say 10 log 10. Yeah. Yeah, so people normally plot this in decibels. And what you see is, okay, yeah, it basically passes everything up to this frequency, and then it kind of goes down like linearly like this. So that's encouraging. Yeah, okay, so then let's see how does this finite impulse response one do if I compute z semicircle feed forward. Actually, let me define a different variable name for this. I'll call this n, or maybe I'll just call this order here. So this is order. So I want to keep this straight here. And then, yeah, this is called n. This is how many samples I'll be using in the feed forward filter, the convolutional filter here. So let me include this in the legend here. I'll say plt.legend feed forward order equals order. And then I'll say feedback n equals what? N. Okay, so let me go ahead and compute that. So z semicircle feed forward. So I will plot that. So I'm going to say here. All right, so I should have called these omegas. My bad. These are the radian frequencies at which I'm evaluating this. So I'm going to say here omegas h is equal to z semicircle feed forward of this impulse response that I came up with here. So what would the transfer function be if I just convolve with that impulse response? And so I can plot that. And let's see what I get. Okay, so this is pretty interesting. Actually, maybe it's a little bit harder to see exactly where the cutoff is when I do it in decibels. Let me go back just to linear units for a second and show you the difference. So yeah, this filter is not nearly as good. You can see it takes a lot longer to go down. So what I could do, I could try to use more terms here. I could say, okay, let me try to use maybe like 40 terms. So I'm really giving it, a lot more time history than the feed forward one. And you see I do, kind of similar. Let's go back to the log scale again. Let's see the difference. So yeah, I mean, okay, maybe this is a little bit better at 40, although it's pretty similar. And look how much more time history I needed to do it with the feed forward one, which is a convolutional filter. So I could convolve with this and I could do okay with 40, but I would only need to look 5 samples in the past for this using the feedback filter. Okay, another practical point I should mention here is if the filter is high enough order, then I may have some practical issues with numerical stability if I try to evaluate the transfer function directly. And so instead, what we can do is use something called second order sections. Basically, the transfer function gets factored into lower order polynomials that are second order. That's not exactly what I did here. I guess I had one of them that was second order here. But yeah, the idea is to factor it into a sequence of lower order filters and evaluate them individually. So to do that, I would say, instead of saying signal.butter with all that, I would instead say signal.butter output equals SOS. So let's say SOS equals signal.butter, the order, and then the cutoff frequency in the right units there. And I would say low pass, and then I would say type equals SOS. Or, whoops, what was it? It wasn't type, it was output equals SOS. Okay. And so that will be fine. And then I wrote a little bit of code ahead of time to plot this. So plot zeros and poles in this case. And I can see here, yeah, I've got, I should have, in this case, 40 zeros and poles. And yeah, but this is like probably overkill. The higher the order, the steeper the cutoff you get. But yeah, this is pretty high. Okay, let me, yeah, also, yeah, if I go ahead and I plot here just to see, this is what the transfer function magnitude looks like on the unit circle. And just to show one more example here, you can also do you can do high pass filters. You can also do band pass filters. So maybe I'll say, you know, I need two frequencies here. So maybe I'll say, okay, I want the band in between 0.1 cycles per sample and 0.2 cycles per sample. And so what I'll do is I'll change this to band pass. And I'll put, now this actually takes a list of the edges of the band that I'm trying to put through here. And so let me make these two plots again and show you the result. And so this is kind of cool here. So yeah, if I look at the response, I say, okay, great. Between 0.1, actually let me make sure I show both edges here. Between 0.1 and 0.2, I'm passing through, and then I cut off. And actually, to really emphasize it, let's zoom in on, I'll say just negative 100 dB to 0. Oh, maybe that was too much. Okay, well, or I should go. I'm trying to get the view right here because it drops it very quickly outside of the pass band. So, oh, whoops, it was 10 log 10. Okay, I'm in decibels. Yes. So let me make the maximum here be 11. There we go. Okay. So anyway, looks very nice. It passes through in the passband. And then you can see with the zeros and poles, what happens is, okay, I've got a bunch of zeros at 1 on the unit circle here. So it's not going to pass things through. The zeros are pulling me down. But then I get closer to the poles, they pull me up. But then there's some other zeros over here at pi that pull me down again. So that's a bandpass filter. And yes, of course, if I put the order down, then I get fewer poles. And the attenuation is not as serious outside of the bandpass filter, so it takes longer to fall off. So that's the trade-off. Oh, and also I should point out, so here the order, I specified the order as 5, but it looks like I have 10 poles instead of 5. That's because, actually, this is a bandpass filter. The order means something a little bit different here. This has been a little bit sneaky behind the scenes. Let me return the result here, and you see, actually, I wasn't lying. This really does have 11 feedback terms, including y of 0, so or y of n. So this really is going to end up. So this is order 10. It's going to end up having 10 poles. I know I said order 5, but actually, in order to make a bandpass filter, you can do it by first making a low pass filter and then making a high pass filter from what's left, doing them one after the other. And the result is like multiplying those two transfer functions together. And so if each one of those transfer functions is order 5, the result will have order 10. Okay, blah, blah, blah. Basically, for bandpass filter, the order is actually twice what you're specifying here. Yeah, so if I'm specifying order 5, I'm going to have 10 delays. If I'm specifying order 40, I'm going to have 80 delays. Let me just check that. So this should have, yeah, so 81 total, including the original lag. So the biggest lag is 80 there. Okay, great. So that's awesome. It's cool to see math work out. But now what I want to do is apply this to audio. I'm doing a lot of analysis, but let's actually apply some of these signals to different audio scenarios. So let's say I was going to take a sample rate of 44,100, maybe 4 seconds of audio, and I'll make a square wave at 440 hertz. So I'll say y is equal to mp.psi cosine of 2 pi ft. Okay, and I listen to that. And it sounds like this. Now, let's say I was going to decimate this, or in other words, let me drop every so many samples. So I'll say here y is equal to y, and I'll drop every fac samples, or in this example, every 2 samples. If I play that back, I should expect to hear something at a higher pitch, actually 1 octave up. But I hear a little bit of badness there. It sounds like some low frequency sneaked in here. And if you remember, this is the result of aliasing. And one thing you can do is make a low pass filter that filters out everything above a certain amount before doing this decimation. So let me go ahead and grab some code that I was working with before to make a lower order low pass filter here. So I'll do it like this. And let me change this to X here because I want to differentiate between the original signal and the filtered signal here. So originally I'll just play, I'll play the signal dropping every other sample, but now I'm going to do a little work to filter this. And so if I think about this, what I realize is, okay, if I haven't done any decimation, then everything can pass through up to the Nyquist rate, which is 0.5 here. But if I am going to drop every other sample and downsample by a factor of 2, then I have to cut out half the frequencies. If I downsample a factor of 3, I have to cut off the top 2/3 of frequencies. So let me set the cutoff frequency to be 0.5 divided by the factor by which I'm downsampling there. And okay, great. So I'll make my Butterworth filter. And then I have this method that I wrote to actually evaluate the filter when it's specified as a transfer function form with these coefficients b and a. So I can say eval filter. So I'll say y is equal to eval filter b a x. Now let me listen to the result of dropping every other sample of this filtered signal. So here's the original. Here's the result now after low pass filtering before taking every other sample. So you don't hear as much of the buzzing. Let's see if we go up in the order a little bit. Let me go up to maybe order 20. Let's see if we hear a difference. I mean, not really. So it turns out, actually, this is already aliasing. It's already captured alias frequencies, getting it at 44,100 hertz. So there's only so much we can do to fix this up. But okay, so that's one application. So for another application, let's load in one of the best remixes ever in history by one of my students, Joe Lyons, in spring 2021. So this is the real DFT. If I listen to this, here's what it sounds like. Whoop. I'll just say SR here.
I repeat.
Will the real DFT please stand up? Please stand up. All right, so my student took some audio from one of my videos and made it into an epic FM tune. But let's say that we were a little bit unlucky, and unfortunately, this came in with some noise. So maybe I'll add a little bit of random noise to this. Let's say plus 0.1 times np.random.random x.size. Let's listen to this now. Oh, that's just noise. I meant to say plus equals. Okay, there we go.
I repeat.
Will the real DFT please stand up? It still sounds pretty crappy though. So one thing I can do is try to apply low pass filter, because noise manifests itself. This random white Gaussian noise manifests itself as white noise in the frequency domain as well. And what that means is it contributes equally to all frequencies. I can compromise and cut out some of the high frequency information and then just retain the low frequency noise here. So let me show you what that is going to do to this. So let me say, okay, I'll use an order 5. Maybe I'll make the cutoff frequency be 0.2. So I'm going to cut off some of the high frequency detail, but let me just listen to how it sounds. So the original sounds like this.
I repeat.
And the filter version sounds like this.
I repeat.
Will the real DFT please stand up? So, I don't know. It sounds a little more like a waterfall. Let me actually cut it down even lower.
I repeat.
Will
Will the real DFT please stand up? Please.
So I don't know. Maybe it sounds better.
I repeat.
Will the real
I do lose some of the fidelity in the higher frequencies though. So this is not the best denoising technique out there, but it's one. All right, and really, you know, the sky's the limit. Once you can start to get down the basic bandpass filters, you can make all kinds of filters. You can design EQs. That's what people in production would call them, to emphasize certain frequencies and de-emphasize others. It all comes down to understanding the poles, where to put the poles to pull certain frequencies up, and where to put the zeros to pull other frequencies down. All right, so I hope you enjoyed that. I hope that was enlightening. I tried to give you the sort of primer that I wish I had had when I was younger. It took me many years of studying in undergrad to understand this stuff. Hopefully I can give you a bit of a shortcut.